Okay, so today we're going to move beyond the simple bits of bonding, the ionic or the covalent, and begin looking at the structures. So rather than just the atom-atom ion basis, what it looks like when they're interacting all together. We run through in separate videos the fact that if your substance is pure, if you've got a pure compound, a pure element, they have different structures depending on the type of bonding, and that affects their properties, their behaviors. So in this little video, we're going to go through ionic compounds, how ionic compounds behave. Then there will be two separate ones on covalent, because covalent molecules, depending on them, will be either simple, like carbon dioxide and water, or giant, like diamond and graphite. And then lastly, we'll look at metallic. So the structure of that substance decides its physical properties. Remember, the chemical properties all come back to that original type of bonding they're making, those electrons on the outer shell, and how they are going to bond. So ionic, what do structures look like in ionic compounds? Well, there's only the one type of structure, a giant ionic structure. When we draw it on a diagram, it tends to look like this, plus, minus, and there are only ions involved. And this is very, very important. As soon as you identify that it is an ionic compound, you can only talk about the behavior of these substances as the behavior of ions, because they are made up entirely of positive and negative ions. And remember, our ionic compound will contain a positive ion from group 1, 2, 3, or the transition metals. So a metal to form a positive ion, and a negative ion from group 5, 6, 7, most of the non-metals, to form a giant ionic lattice. And all the word lattice means is a repeating unit, and uniform structure where it's going over and over again, like shown in the diagram. And we call these giant ionic lattices a salt. So all ionic compounds form salts, giant ionic lattices. Obviously, this diagram really kind of gives you a 2D image. So to show you a little bit of where we're at, if that makes sense, we can have a little look at this model. So we will have our silver one as a positive ion, our yellows as negative ions. So we have our positive ion, obviously plus, minus, that's the attraction. So you could see in the 3D structure, if we had all of the pieces, that the positive metal ion would be surrounded by 6 negative anions, negative non-metal ions. So one above, there would be one below, one either side, one behind it, and one in front of it. Likewise, if we were the negative ion here, this would have a metal ion, positive ion this side, above, below. So each negative ion would be surrounded by 6 other ions as well. Now it's hard to see that in the picture, the 2D diagram, because obviously you can't see in front and behind, but we can show it in diagrams. So you could show the positive sodium, the negative chloride like this, or you could show it as a 3D structure, which is a bit more like this one, our 3D structure here. However, it's very, very hard to draw that 3D structure in an exam, so you would need to remember to talk about how each positive ion has 6 surrounding negative ions, each negative ion has 6 surrounding positive ions. And as we talked about, the positive and negative ions strongly attract each other, our electrostatic attraction, to make the regular crystal structure, and we call that the lattice. That repeating structure is a lattice. So because we have this lattice, the idea is that there are very strong bonds between the ions. Remember, we can only talk about ions. There are only ions in an ionic compound. So they have high melting and boiling points, and that's because it's very difficult to pull apart the positives and the negatives holding on to one another. So in between positive and negative ions, you have that strong electrostatic force, and because there is just a giant repeating structure over and over and over again, to get this to melt, you have to break every single one of these strong ionic bonds. So for example, sodium chloride melts at over 800 degrees centigrade. You need to hotter than a Bunsen to get sodium chloride to melt. And it's because we have to break all of those bonds to turn it into a liquid. So all ionic structures, all giant ionic lattices, have high melting and boiling points because of the strong bonds between the ions. Because ionic compounds are made of charged ions, obviously we have our positive and our negative ion, they conduct electricity if the ions can move. So while our ions are in our 3D structure, while they're held together in a solid, thinking back to particle theory, these ions are only vibrating. They're staying in the spot. They can't move past one another. So there is no way for them to conduct the electricity. They're held in place by the forces between one another. So solid ionic compounds will not conduct electricity. However, if we can melt them, we can make them molten, so we get it hot enough above that high melting point. Once it's a liquid, like all liquids, the particles are able to move around, they're able to move past one another, and then it can conduct electricity because the ions will carry the charge as they move around. Likewise, if you can dissolve the ionic salt, if you can get it to dissolve into water, the ions again can move around. We've split off the ions from their giant lattice, and they're now moving around in between the water molecules, and they are therefore able to conduct electricity once dissolved. So this is obviously a much lower temperature than this, so this is the more favourable way to get an ionic compound to conduct electricity, but not all ionic compounds dissolve, so preferable, but sometimes you do have to make them molten. You would have to melt them to get them to conduct. So molten compounds conduct, as this shows. You've got your ions. Once they are a liquid, they can move past. You put the electrical current on and the particles will move quite happily. And this is the foundation of electrolysis that we will look at later in the course. When you put the salt into water, again, the water molecules, the H2O molecules, pull the ions apart to make a solution, and the ions can move around again. It's important to note, guys, that the water, the H2O molecule, has no charge on it. It's not positive or negative, it's a covalent molecule, so it cannot conduct electricity. The water will not conduct the electricity at all. It is the salt, the ions that have dissolved into the water that allows it to conduct electricity. So you have to have the positively and negatively charged ions dissolved in the water to conduct any electricity. And we can see this from this little diagram. If we have pure water, solid salt, or a salt solution, dissolved salt, our pure water molecules will not conduct electricity. Our solid salt, our ionic lattice, cannot conduct electricity. This one because there is no ions, and this one because the ions cannot move. But if we mix the two together, if we dissolve them, the positive and the negative ions are mixed in to the water molecules. The water molecules are allowing them to move, so you will get electricity conducted in that one. So dissolved ionic compounds conduct electricity, but only when dissolved. So in summary, for our giant ionic structures, there are only ions in our giant ionic lattices. So you cannot talk about atoms or particles or electrons. There are only ions. The electrons have already moved, like we looked at when we did ionic bonding. They have transferred from one atom to the other to form the ions in the first place. So the electrons are not moving anymore. Only the ions can move when you dissolve or melt them. They have a crystal lattice, a repeating structure, and most dissolve in water like sodium chloride. So if we are describing an ionic compound, this is what we would talk about. We would talk about there being 6 negatives around a positive ion or 6 positive ions around a negative ion, the repeating structure of the lattice. If we were going to talk about the properties, we would talk about what property an giant ionic structure has and the reasons behind it. So our high melting boiling point is because of the strong bonds between ions. Note, it's that key word ions because we are ionic. And they can conduct electricity. When they're solid, it will not work because the ions cannot move. But when molten or dissolved, it will conduct electricity because the ions can move to carry the current. Either they can move around one another because they're a liquid, or they can move because the water molecules have allowed them to separate. So giant ionic structures, the only form of ionic structures that exist, high melting point and boiling points. conduct when molten and dissolved, but not when a solid. So next time, giant covalent structures.